Sorry for the delayed start. Good day. Hope things are well. Plan for today is to look at some of the more in depth with the properties of electrical resistance, because what determines an object's electrical resistance. Well, we actually looked at one of the formulas yesterday, so we'll just go into more detail there. And depending on how long that takes, we'll probably begin looking at the circuit stuff that we'll keep doing later in the week. Let me know if there are any questions about anything we've talked about thus far or any existing assignments, anything on your mind, and I'll get presentation set up. All right. So, yesterday we began talking about electrical current, what it is, some of the aspects that affect it. Current, the amount of electricity, the amount of charge per second that flows through something is determined not only by the voltage that exists to push the electricity to move, it also depends on the resistance of what the electricity is currently flowing through. Certain things resist more than others. If something has high resistance, that tends to slow down or prevent current from traveling through it. Rubber's a very good resistor, so electricity doesn't flow through it very well if it flows through it at all. Other good insulators include, but are not limited to, styrofoam and air. As it happens, air is a very good electrical insulator, and that's one reason why just touching a wall outlet doesn't get you electrocuted. It's because you're really touching air between you and the prongs inside, and the air is a good insulator. So, we discussed Ohm's law down here. I equals V over R, alternatively V over IR, as the relationship between these three things, the three parts of kind of current flow that make up a circuit. Right now we're going to focus specifically on resistance, because there's a few formulas that determine what an object's resistance should be, and understanding them is important for getting an idea of why certain machines behave a certain way, or why certain materials behave a certain way. We glanced at this other formula circled up here yesterday. An object's resistance is equal to this constant here, which is another one of those constants where it depends on the material, and you'd have a table to look it up, and you don't have to memorize any of them. That constant represents the electrical resistivity constant of the material in question. So say you were building a cable out of copper. You're building specifically a copper wire. Then you wanted to know how much resistance it had. You'd go to the table and look up that constant for copper. So resistance equals resistivity constant times the length of the object divided by the cross-sectional surface area of the object. This formula works a lot like the thermal power formula. The same or similar variables affect the rate at which thermal energy flows through something, and that affect the rate at which electrical current, electrical energy flows through something. Which makes an amount of sense, because things that tend to be good thermal conductors also tend to be good electrical conductors. Metal conducts heat and electricity very easily. Water might be slow to warm up, but it conducts heat at a pretty reasonable rate, and water can be said to conduct electricity. So, And similarly, things that are good electrical insulators tend to be good thermal insulators. Rubber, plastic, styrofoam, air, all those things are very good thermal and electrical insulators. So the two properties, they aren't just, like, their formulas aren't just similar, they are similar properties, period. Odds are if something resists one, it will resist the other. So, there's, in addition to these elements, well, actually, I'm getting a little ahead of myself. That constant there, the resistivity constant rho, there is a table that tells us the resistivity constant of various materials. So this is the chart that will be, this is the chart that homework will refer to. This is the chart that will be in notes and formula sheets, etc. This first column here is the resistivity, that is the constant in question, ohms per meter, the resistance of the object per how long it is, of various materials. And looking on this particular list, we can see that all the metals here, the list starts with metals, they all have very low resistivity constants. They're all, to the factor of times 10 to the negative 8th. Meanwhile, the highest values on this table, at values approaching times 10 to the negative 13th, 14th, 15th, 16th, are glass, rubber, sulfur, weirdly, I wasn't expecting that one, and fused quartz. Very good resistors, just based on what they're made out of. I didn't know that about quartz or sulfur, actually. Not off the top of my head. So, like with pretty much every chapter in this class, new table for various constants of various different materials. Something to note about this particular table, this column of constants will work just fine, jumping around, sorry, for this formula right here. If you had some length of copper wire, you could figure out its electrical resistance by looking up the value of copper, multiplying that by its length in meters, divided by its cross-sectional surface area in meters squared. Which, again, if you were doing that for a rounded wire, if this was like the end of the round wire, the cross-sectional area would be the area of this circle right here. Say, we did some similar things for thermal conductivity, I believe. Now, if you were to look at this table, you can look up, say, the entry for copper right here, but there's something to note about the values on this particular chart. There's a second column over here, and the reason that there's this extra column is that all of these different resistivity coefficients here, this first column, all of these values are only true at 20 degrees Celsius. Have you ever noticed that electronics maybe stop working as well when they overheat? Could be a computer, could be something dumber like even a vacuum cleaner, frankly. Most commercial electronics, when they get too hot, they don't usually work quite right, and eventually they hit a certain risk of overheating completely and just not working. That's because as objects get warmer, their resistivity constant changes. The resistance of the entire object involved changes as an object gets warmer. As a general rule, and I'm hoping that your life experience kind of backs this up, the hotter things are, the more they resist, the less efficient it is electrically. And again, that's why machines can overheat. The colder something is, the better it conducts electricity, the more efficient the electricity can move through that particular object. And this is why most computers or things like that have cooling systems in them, specifically to keep everything in there cold, not melting, and as electrically efficient as possible. computer gets too hot, it risks slowing down. If it gets way too hot, it risks shorting out and melting, frankly. So this first column right here, these values only work at 20 degrees Celsius. They will all increase as temperature increases for that particular material. This second column over here, temperature coefficient of resistivity, this column is designed to help us better understand how this first column is going to change as the object's temperature increases. So there's this second column here, and the way that we use the values in this column is to adjust, to change the original value for the constant in question. So again, I'll tab back to the resistance formula. Resistance equals resistivity constant times object length divided by cross-sectional surface area. The value that you plug into this formula needs to be correct for its current temperature. So in order to... This column only lists at 20 degrees because that's kind of the standard. In order to change that value to be correct for the current temperature, we have a separate formula here. Current resistivity constant equals baseline resistivity constant times open bracket 1 plus temperature coefficient times the difference in temperature from the baseline, close parentheses, close bracket. It looks kind of funky. I'm going to step through what each part kind of means and represents for us. The purpose of this formula is to take the standard 20 degree value right here and then adjust it to what it needs to be. So in this formula, rho subscript 0, rho naught, that represents the baseline. That's the 20 degree temperature the 20 degree resistivity constant that the chart is used to operating from. And the rest of the formula exists to modify the 20 degree form constant into whatever final form it needs to be for its current temperature. So note, within the brackets here, 1 plus alpha times the difference in temperature from the baseline. Both of the terms here that have a subscript 0, we have thermal conductivity, we have resistance constant, naught, and temperature, naught. Those both represent the baseline state. On this particular chart, that baseline state is what is the resistivity at 20 degrees Celsius. So when using this formula in conjunction with that specific chart, the rho naught here is the resistivity constant at 20 degrees. That's the normal standard 20 degree resistivity constant right there. And since that standard resistivity constant is calibrated for 20 degrees Celsius, 20 degrees Celsius is automatically what goes in here for standard operating baseline temperature. And then everything else you plug into the formula is just there to offset it from that baseline temperature to better represent its electrical properties at its present temperature. So notice, if, say, you were using this formula, you wanted to confirm what something's thermal resistivity was at 20 degrees. 20 degrees is our baseline. If you plugged in 20 degrees as its current temperature, 20 minus 20 would be 0. So 0 times alpha is 0. So that kind of eliminates the temperature change constant. 1 plus 0 is 1. 1 times the baseline constant would give you the original baseline constant again. So this formula shows that as long as we know what our baseline is, so this is set from 20 degrees, as long as you're at 20 degrees, that formula backs up that this column here is the resistivity constant at that temperature. So if you were working a question where something was just at 20 degrees Celsius and you wanted to find its electrical resistivity at that temperature, this formula says that you don't need to change that value. Excuse me. Whatever that table gives you for 20 degrees, you can use it at 20 degrees without needing to use this formula to change it, because this formula wouldn't change it if you plugged in 20 degrees as the baseline and as the current temperature. If the temperature you plug in is not 20 degrees, then this temperature difference term doesn't become 0, and that's when the alpha term starts to matter. So when the temperature is different from 20 degrees, then you look at the table for the alpha value, the temperature coefficient of resistivity. This represents how much the material in question changes its resistivity with changes in temperature. And that's the value that you plug in for alpha. So if, hypothetically, we wanted to know the resistivity of a copper wire at 25 degrees Celsius, we would need the baseline constant for copper, we would need the temperature coefficient for copper, those would plug in for rho naught and alpha, and we'd plug in 25 as our final and 20 as our initial. How much is resistance constant increase for an increase in 5 degrees? So, things to remember. Resistance tends to increase with temperature increase. Hotter things get, the more likely they are to resist more, the slower current travels through them, the more likely your machine is to short out and eventually melt. Questions, comments, needs, concerns, etc., let me know. I'm actually going to pause real quick because I left my water in the other room, so I'm going to get that while I take a quick break from speaking for a minute. I'll be right back. Let me know if you have any questions when I return. So if there are no questions, then let's look at a few examples that kind of combine these two resistivity formulas together, in addition to possibly some work with Ohm's law as well. So, let's make, first sample question. We're going to make a resistor out of a sample of tungsten. Tungsten, historically speaking, is a metal that's been used pretty commonly in electrical practices. Namely, most old school incandescent filament light bulbs, the filament inside the actual squiggly piece of metal that glows when you run electricity through it, that's made out of tungsten. It's very resistant to changes in its own temperature, which is good because if it wasn't, it would overheat and eventually explode. So we're going to make a resistor out of this particular material. Our resistor is going to be 3.25 centimeters long. It is a square cross section, so for simplicity's sake, this isn't a round wire. It's a blocky square wire, which can exist. It'll make calculating its cross-sectional surface area a little bit easier. So we know that cross-section, it's 0.1 millimeters by 0.01 millimeters by 0.01 millimeters. First question, what is the resistance of our resistor at 20 degrees Celsius? So that's again going to use the standard unmodified values from that table. We will then calculate how much current it will pass through that particular resistor if we wire it up to 120 volts. And then we'll see what happens to that resistor and the current as its temperature increases over time. We'll heat it up from our starting temperature of 20 degrees to a final temperature of 3,000 Kelvin, which is very hot. So this will be what we'll be looking at together. So, first up, what is the resistance of your resistor at 20 degrees Celsius? So, I went ahead, for completeness sake, and I start with resistance equals resistivity constant times length divided by cross-sectional surface area. For completeness sake, I did write in the entire modification section just to show how it will kind of collapse in on itself and go away if you're staying at your starting temperature, at your baseline temperature. So, excuse me, looking at, we'll just tab back to the constant table real fast. Looking on this list, properties of tungsten. Resistivity of tungsten is 5.6 times 10 to the negative 8th ohms per meter. And its temperature coefficient is 4.5 times 10 to the negative 3rd. So those are the constants for rho naught and for alpha. And again, since this resistivity is based at 20 degrees, it doesn't need to change at all. This resistivity will stay the same. The reason I included the rest of the sort of the constant change formula was just to show and demonstrate that if it's still at 20 degrees, then this whole term here just becomes 0, and then you're just multiplying 1 by the baseline resistivity. It doesn't change at all. So I'm trying to show that in the notes. So our 20 degree resistivity for tungsten will remain unchanged. So we'll just keep the same constant from the chart. So we'll have our resistivity constant times our length for this resistor, 3.25 centimeters converted to meters, and our cross-sectional square surface area. 0.01 millimeters times 0.01 millimeters is 1.10 times 10 to the negative 10th meters squared. This particular formula, this particular kind of section of the class, it's important to keep track of what units of length that you're using, because most wires, most resistors tend to be really small. Their surface areas tend to be really small. Occasionally their length is really small. Like the commercial resistors that I showed you in lab the other week are very, very tiny. They physically don't have a lot of length inside of them. So sample questions, homework questions might often give you lengths in centimeters, lengths in millimeters. Make sure to convert them before you use them in the formula. So at our baseline temperature of 20 degrees, resistivity constant times length divided by cross-sectional area gives us a resistance of 18.2 ohms. That's comparatively low resistance. You could buy a resistor at a store for an electronics project that had a resistance of that value. That's probably less than a actual electronic device, but more than a normal wire by itself would be. So we've constructed a resistor. It has a resistance, and we know what that value is. Now that we know its resistance, if we were to wire that resistor into a 120 volt circuit, we can use Ohm's law, V equals IR, to determine how much current will flow through it. So this would be if we built a 120 volt circuit. So here's our 120 volt power supply. Here is our resistor. This little squiggly line here is the symbol for a resistor in a circuit. It's designed to be very, very visually similar from the symbol for a capacitor. Every different possible thing on a circuit diagram has a different symbol. And the squiggly line kind of looks like the one on Charlie Brown's shirt. is the symbol for a resistor. So this is basically the circuit that we're going to build. Just our one resistor wired directly into our 120 volts. This voltage will be able to push a certain amount of current through this resistor. So 120 equals current times 18.2. That amount of current would be about 6.95 amps. Again, safety reminder, that's a lot of amps. That many amps will kill you. So this is not a very safely designed circuit. Would not recommend this. But that's the first two parts solved. We found the baseline resistance of the piece of tungsten, and we know how much current will flow through it. Now, as with most things, most machines, having it turned on, having electricity run through it, is going to increase its temperature. I mentioned that tungsten, the element in question here, is the material that was used for light bulb filaments, and possibly still is if anyone's manufacturing filament bulbs anymore. One thing about those bulbs is, as soon as you turn it on, it starts emitting light. But as soon as it turns on, you also don't want to touch the light bulb because it gets really, really hot. Running current through anything will increase its temperature, and in the case of tungsten, specifically just a single filament with a ton of volts running through it and a ton of current running through it. Again, 6 amps is huge. We tend to operate in the milliamps, so this is a ton of current. This filament is going to heat up super fast. And now we're going to see what happens to its resistance and the current in the circuit if its temperature increases to 3000 Kelvin, which, running this much current and this much voltage through a tiny piece of tungsten, yeah, it can get this hot. Running electric current through some things is one way that certain manufacturing processes heat up materials to be able to melt and smelt and forge and, reshape them using electricity to heat them quickly. So, our temperature is going to increase, which means that we now need to use the coefficient changing formula to adjust our electrical resistivity constant here. So, this piece of the formula, we still have R equals rho times length divided by area, but now we're going to be using the full modification portion of the rho formula to change it from its baseline rho. Said baseline is the same. It's still tungsten, so at 20 degrees, it's still 5.6 times 10 to the negative 8th. But now, we're going to plug in our alpha. Again, from that table from earlier, the alpha temperature coefficient for tungsten is 4.5 times 10 to the negative 3rd. And now we're going to increase its temperature from 20 Celsius to 3000 Kelvin. This is another one of those cases where you can get away with using Celsius, since this is basically a change in temperature. Any temperature minus another temperature in the same scale is basically a delta T, so we can use Celsius here, but only if both units are Celsius. And we were given 3000 Kelvin. So what I've done here is I converted 3000 Kelvin to 2727 Celsius and then plugged it in with the baseline 20 degrees Celsius. So that's why it doesn't say 3000, because we need to convert it to Celsius first. So it's a long string of things to end up multiplying and things, but we have everything we need to figure out what the new resistance is at this new temperature. The length and area remain unchanged, so those values are the same as they were before. Our new final resistance at this new elevated temperature is approximately 240 ohms, which is a pretty big increase from 18.2. Granted, 240 ohms still isn't a lot of resistance, technically speaking, But it is a, in this particular case, let me check real fast. 9 divided by 18.2. That's a, excuse me. It's times 13. It's 13 times bigger. The resistance is 13 times bigger at that elevated temperature. And ultimately, because the resistance is 13 times bigger, the current is going to end up being about 13 times smaller. If we take our new resistance and plug it back into Ohm's law, V equals IR, voltage doesn't change, but our resistance did. Our new final current would be only half an amp. So we went from about a little more than 6.5 amps down to just half an amp. That is still a large and frankly irresponsible amount of electrical current, but it dropped again by 13 times, like how the resistance increased by 13 times. This is what happens in your machines. The resistance of all the internal components rises. As the resistance rises, the actual current flowing through the wires will go down because the current is flowing slower. It takes more effort to force itself through the components of the machine. The current drops, and if it drops too low, then the machine might just power off completely. All devices need a certain amount of energy per unit time in order to stay active. Every different machine has a different wattage telling you the energy it needs per unit time. If the current dips too low and it's not getting energy fast enough, it might shut down. That's the danger you run into. And tragically, we see here that increasing the temperature can have a pretty dramatic effect. Unfortunately, the simple act of running electricity through something tends to increase its temperature. When you electrocute something, you're literally sending coursing electrons with a bunch of energy through that object, and those electrons leave energy behind. I mentioned yesterday what happens to trees when they get struck by lightning. The electricity starts moving through the wood of the tree. Every single one of those electrons is colliding with the particles that make up the tree. That's leaving energy behind in the tree. And so the tree heats up and burns and maybe even explodes. Running current through things inherently makes them warmer because there's literally moving electrons leaving energy behind in them. And as a result of that, by the act of having a machine on, it's going to start warming up. And so that's why most dedicated, high-intensity machines need to have coolant systems. Your phone and your computer and your car even have fans in them and coolant to try to mitigate that heat gain just from the act of being powered on. Turns out you can't even avoid friction when you're talking about electricity, because electricity moves through things, it leaves energy behind. It's basically the same thing as friction again. You can't escape it, tragically. Let's look at another example or two utilizing these properties before we break for today. I'm just checking my notes real quick. So, I meant to do this example first. My mistake. This one is just standard resistance at 20 degrees Celsius. I meant to do this one first. Sorry about that. Notes contain another example of just utilizing R equals rho times L over A. In this specific case, as just an additional example, you're setting up a lab. You have equipment that needs 2.5 amps of current. You're going to supply 100 volts to it, and you're connecting everything using cables of a certain thickness. If you assume constant temperature of 20 degrees Celsius, how long must your cable be for the 20 amps to specifically have 2.5 amps moving through it. Wires do have resistance, technically speaking. Every single component in a circuit board has some amount of resistance to it. We build like actual wires out of things like copper because they have very little resistance. You don't usually want the wires having big resistance because then they'll overheat faster, and that makes it harder to get current through the machine to the actual parts that need the electricity. But the wires themselves do have resistance. Everything technically does. You just try to make the wires have as small a resistance as possible. So in this particular lab setting, if we have 100 volts, we need 2.5 amps. We can figure out that the wire would need to be 40 ohm resistor in order to make that work correctly. We can plug 40 ohms in as... Sorry, the puppy is whining. We can plug that 40 ohms into R here. And we know wires are made out of copper. We know how thick they are, so we can figure out what their cross-sectional area is, assuming that they're round. And we can just solve for how long the cable would need to be in order for it to have a 40 ohm resistance. The answer is very, very long. 185,000 meters of cable. Again, copper has very low resistance, which is a good thing. And this just means that if you need to make a resistor, don't use copper, because it will be incredibly long. Okay. Penny. Where's your toy? Sorry. All right. Questions, comments, concerns, etc. Please let me know about any of these formulas or sample questions. Couple of things to note before we... We'll just glance at a few more things today, and then we'll save all the math and heavy concepts for tomorrow. Some things to note. Electricity is super lazy. It always follows the path of least resistance, which is why the rubber coating on wires is able to protect you from being shocked. Say you are, building an electrical system, you've coated the wires in rubber, and then you grab hold of one of those rubberized cables. By grabbing the cable, and standing on the ground, you've technically formed you're technically part of the circuit now because you are touching the circuit. There is a chance for electricity to conduct into your hand because of what you're touching, just by grabbing hold of the rubber cable. But because the cable is coated specifically in rubber, and rubber has very high resistance, the electricity is not really going to want to travel through the rubber to go into you and into the ground. Electricity follows the path of least resistance, and that's why it stays in the wire. If you build a circuit out of, copper wires and other components, then the copper wires and the components of the circuit have less resistance than the rubber does. And as a result, the electricity wants to stay in the circuit, wants to keep moving through the objects that resist it the least. This is why the rubber on wires protects you, and it's also why birds can stand on power lines without getting zapped. I am not an artist even when I'm actually using my hands to draw. I'm even worse with a mouse. This is why birds can stand on power lines safely. As they sit on the power line, they have become part of the circuit. Like, it would be possible, electricity could either travel through the wire or it could travel up one of their legs, through their bodies, and out the other leg to continue moving through the rest of the wire. But as long as the wire is coated in rubber, it would take so much more effort to move through the rubber and through the bird that it's just not worth it. It's much easier to continue moving through the metal of the wire because it has less resistance. Electricity always follows the path of least resistance, or it does its best to follow the path of least resistance. It is still possible for some current to exit the rubber and travel into the bird or into your hand if you were touching the cable. But how much of it will do that depends on how much effort that would take. As we start looking at circuits in the coming days, we're going to talk about specifically how the electric current kind of gets divided up in a situation where it could choose one of two different pathways. Current will always prefer the path of least resistance, which literally is the path that has the smallest resistors on it. Again, the copper in the wire is the smaller resistor when compared to the rubber on the wire. But it is still possible for some currents to still move out of the wire and through you. It might not be a lot, but that's still proportional to the current in the wire in the first place. So even though a cable might be coated in rubber, that still doesn't make it 100% safe to touch. Because, like the bird on the line here, you have become part of the circuit. You've become a parallel branch in the circuit. And that still leaves open the possibility of some of the current traveling through you, even though most of it's going to take the path of least resistance. Which is why having very extreme amounts of caution in electrical situations, even when things should be safe, is very important. And it's why we work in our lab setting with super low voltages and super low currents, just for the sake of safety. So, electricity is lazy. One more tangent thought to that fact. One related idea to the idea of electricity being lazy. I'm going to erase my awful bird drawing real quick to make room for a different awful drawing. So this is a poorly drawn cloud. And this is a poorly drawn tree. You've seen lightning strikes before. Lightning happens when a massive amount of charge is built up on a cloud via friction. So the clouds rub past each other, the wind blows air molecules onto and through the cloud, and so via friction the cloud builds up a ton of excess electrons. It has a huge net negative charge right now. Those electrons don't want to be anywhere near each other, but they need something to conduct through in order to exit the cloud. And sometimes it conducts through the air to hit this tree down here. Now, air is a very good insulator. Air has very good resistance, and this is why usually you can move your hand close to a charged object without getting shocked. Air is a good insulator. It's not a very good conductor, and so electricity has a hard time conducting through it. But lightning, when a cloud has built up a huge amount of charge, those electrons don't want to be anywhere near each other. They are so desperate to get away from each other that they will conduct through the air, through a tremendous distance to get from the cloud to the tree, just to escape each other. They will go through the huge resistance of the atmosphere just to escape being trapped together inside of that cloud. The resistance of the atmosphere is tremendous. So the amount of voltage here, the amount of power needed to make that happen is gigantic. The voltage needed to push current through the atmosphere to get to that tree is astounding, and that's the primary reason why lightning is dangerous. Lightning only happens in the first place when the voltage is big enough to overcome the resistance of the atmosphere. And granted, voltage is not the most dangerous part of electricity, but high voltages form high currents. High current, which lightning is, can kill you. So I find that very impressive and very terrifying about lightning whenever students ask me about it. So in general, try not to be the tallest object in a lightning storm or the most positively charged object in a lightning storm. But if hypothetically you could not avoid being electrocuted, being struck by lightning, there is something you can do to try to keep yourself safe. In the past, when humans have been struck by lightning, the thing that keeps them safe is if the current doesn't travel through their brain and doesn't travel through their heart. Those are the two things that you don't want to get shocked, because they're the two things that, if they stop working, will kill you the fastest. Electricity is lazy. And if you are standing on dirt, on the ground, any electricity that enters you wants to go into the ground, because the ground is very neutrally charged, which, from the perspective of an electron, makes it the ideal place to go. To try to guarantee that electricity doesn't travel through your brain or your heart, you want the lightning to strike your right hand and exit through your right foot. You literally want to stand on your right foot and make sure the lightning enters your right hand, because that will form a direct path of least resistance from your hand to your right foot and then into the ground. You don't want lightning to enter one hand and exit the other, because that'll take it through your heart. You also don't want it to enter your head, because that'll automatically take it through your brain. So, I'm not advertising being struck by lightning, but if, hypothetically, you were about to, doing this is possibly the safest way to not make sure one of those two vital organs doesn't get zapped. All right. Those were a few tangents there that I just think are facts worth knowing. Next time, we're going to be looking at circuits again. We've already looked at how capacitors work in a circuit. And next time, we're going to talk about how resistors work in a circuit. And we'll have our usual daily break here. Let me know if you have any questions. If you do not, then I will see you tomorrow.